Thank you, Professor Chakraborty, for inviting me. I'm going to discuss about robust tracking control of wheeled mobile robot and event trigger design. You have encountered this block diagram in any textbook, where you can see that the sensor. So where you can see that the measurement is sampled at a regular interval of time or periodically, and then it is given to the controller. Controller, based on his algorithm, is completely and the computation done is also periodically, and this whole process will be monitored by a clock or synchronized by a clock. And then as most of the actuators are continuous, then a whole circuit will be there to make this discrete control signal in continuous manner to the plant. So this is very usual classical digital control system we know. So some of the observation we can make for this classical digital control system, they are basically, first thing is that the control is updated periodically in time. Not only the control is updated periodically in time, the data from the sensors we are sending to the controller, that is also periodically we are measuring. And it demands a dedicated, reliable feedback channel to send the plant information at periodic instants. We are sending this data through a dedicated channel. That is the approach in classical control theory we are doing. And and also you can see that in classical control implementation, making the processor work in a multitask environment has always been an important concern. So we are thinking that a processor should not be dedicated for only to compute the control for a particular system. If in a situation it is required to share this processor for other tasks, we may allow that one. So that's why always it has been a concern that how we can reduce the control computation, as well as how the channel through which we are sending the data for the measurement, as well as the control signal we are sending to the process, how we can reduce that. So that's why it is demandable that it is always desirable to minimize the control update in digital implementation by limiting the sensor and control computation to only when the system needs attention. Means whenever the system needs attention, then only we are going to update the control signal, and that will save resources in different way that we will come a little bit later. But another important thing is that for the classical setup is that even if we are accepting the periodic paradigm, means if we are going to sample the signal periodically and also the control is updated periodically, even if the question arises that how we will choose the sampling period, that is an important question. And about that, I'm going to refer one Ask the Expert in Control System magazine. So one reader has asked that, as my first assignment as a control engineer, my supervisor has tasked me with developing specification for a digital control system. Do you have any advice on how I should select the sampling frequency? So answer of this question is given by Professor Franklin, and you maybe read his book as a digital control system. What answer he is giving that, you see, sample as fast as project manager's technology and money permit. Second thing is that follow the guidelines given in standard textbook, that is based on the time period, time constant of the system. And third thing is that select a reasonable rate and explore other choices by simulation. What I want to point out that there will be no, it is a basically heuristic rule. You have to decide. A designer has to select that what should be the sampling rate to send the data. So with this scenario, another demand is that now you will find that nowadays we are talking about network control system, where you will find that in classical control, what we have seen that a dedicated channel is used to send the data to the controller, as well as from the controller to process. But nowadays you will find that instead of dedicated channel, we will use a communication network which will be shared by several other control systems also. And then the challenge is that this network, communication network, if it is congested, then the overall performance of the control system may be deteriorated, because at that time the network imposed imperfections also is going to be a very important role, because we will find that the packet loss and then the delay, all these things are going to happen. So now the question is that in this scenario, how we can reduce the transfer of message rate. That's why Kiran was telling that how rarely we can update the control, and then only we can free this channel, and this channel can be used for other purposes also. Means the bandwidth requirement will be not a constraint. And another important thing is that also we want to resolve that what way the sampling will be done. So in this scenario, we are proposing that, or means it has been proposed, one of the alternative solution is that why not we will go for event-based approach, where what we want to do that we will not do the sampling based on time. Instead of that, we will do the sampling based on event. Okay, and it is having huge application in the network control system, Internet of Things, and the cyber physical system. And most importantly, event-driven control is closer to how a human behaves as a controller. It is very common to human behavior, because suppose you are going to control a control valve to maintain the level of a tank, human driven. So now, is it not required to drive all the time to close or open the valve? What you are doing, you are driven by the event, because whenever you are finding that the level is going to cross the maximum limit, then only you are executing the control action. So that's why the same philosophy will be used here also, that whenever you will find that you are destabilizing, or you are very far from the tracking objective, then only you are going to update. Otherwise, update the control law, or otherwise you are going to send the previous control signal, such that the control computation will be lesser, as well as periodically. Whenever you are not sending the data periodically, then your channel also will be going to be free, which can be used for other applications also. So that's why in the scenario of network control system, you can think that now only we should not focus on the control. We have to integrate the control, computation, and communication. These three C's are very important, that we have to combine or integrate the control, computation, and communication, which that event trigger is going to do. So here, this is the thing what I want to mean, that you see in periodic sampling, what we are doing the sample in time base, means once T0 is known, then all the future sequences of sampling sequences are known to you. But in case of event-based sampling, we want to do in the y-axis, based on the event, we are going to generate, or we are going to take the sample. So with this, I want to show you the block diagram of, in general, what would the event-triggered control system. Here you can see that with the sensor, one additional thing you can see, that triggering mechanism. We used to say that this sensor is now become the smart sensor, only it is not going to measure, it having some computational capability also. Means a triggering mechanism will be developed, and based on this measurement, this triggering mechanism is going to check whether to sample or not to sample. So this is the basic philosophy for the event-triggered setup. And this communication network may be the wireless or a common network to which other control systems are also shared. So now, to motivate you people, that I am taking a small example such that you can understand it. So you see, I have taken a simple continuous plan, that is xt equal to ut, and it is a scalar plan. My objective is to find the control such that asymptotically the xt is going to be 0. So with this, you see, we can propose a control law of simple state feedback control ut equal to minus xt, and if you substitute, the closed loop system will become this. And if you take a Lyapunov function from which you can show that the system is globally exponentially stable. Now, what we want to do, that this is the time trigger approach, we can say. Now what I want, that we want to design this, or we want to stabilize the system using event triggered execution, and no longer this triggering sequences will be periodic. So now, to define the execution rule or the triggering rule, what we are doing, we are introducing a sampling error or measurement error that et equal to xt minus xtk, that is the current state of the system minus the last measured state. And the control law we are proposing based on this sample signal, that is ut equal to minus x into tk. And now we are, with this control law, we are computing the closed loop system. And if you compute the closed loop system, then we are finding that one additional term is there, that is et, which is the measurement error. And now if we want to prove the stability of this system, then again we have taken the same Lyapunov function v equal to half x square, and we arrived to this inequality, and we are finding that if we are taking the inequality mod of et less than equal to k into xt, then we can able to prove that g dot x will be less than equal to this 1 minus k into tv when 1 minus k greater than 0. And what I want to mean that this could be the stabilizing law, and this inequality can be used for the update of the control signal. Okay, so that's why here you will find that with this triggering law, we have tried to plot and for the different values of k, and you can see that if the k is chosen little bit of higher, means that is k equal to 0.8, and this black curve is the continuous performance, and for k equal to 0.2, means here what is the role of k? K is the stabilizing rule. You can see here the design parameter sitting in the triggering law, and you can see that almost similar kind of performance we are getting. And as earlier speaker pointed out, that you can see that the control is kept constant, and after that it is updated, something like this. And most important thing is the cumulative triggering. If you choose k equal to 0.8, then only this much of cumulative triggering you are doing, means this many times you are aggregatedly updating the control law, which is significantly less compared to even k equal to 0.2 and the continuous case. So here what we want to point out that what is a challenge in event triggering setup? You can say that, okay, I can do the aperiodic sampling. What is the problem? Problem is that, or challenge is that, even if you are doing aperiodic sampling, fine, but you have to ensure that even if you are updating the control law aperiodically, how you will ensure the overall stability of the system without sacrificing the performance of the system. So that you have to see, and with this I'm going to start the main part of my discussion, that what is the, so here you will discuss about the event triggered sliding mode control of two-wheel mobile robots. I guess that you people have the idea of, and by changing the torque between the differential drive between the two wheels, we can go up forward direction and the backward direction, and we can change its heading angle, but we cannot slip sidewise. So now we can model a kinematic model of wheeled mobile robot by simple this equation number 1, where we have taken some disturbances which is entering through the control input, that is v and omega. So here in the kinematic model, we are telling that this x, y and theta are the system states, and v and omega are the input to the system. Meaning this linear velocity and the angular velocity are the inputs to the system, and it is an under-actuated system. And now my objective is that to track a desired trajectory. So to do that, we have introduced a reference trajectory, which is a model-based reference trajectory, and exactly the same model we have taken, and it can be understood in the next slide. Here you can think that we have a virtual robot, and as this virtual robot is going to move, the actual robot is going to follow this the path generated by the reference model. So that's why the reference model is exactly same as the actual system, and then we are trying to convert this tracking problem to the stabilization problem. So that's why we have introduced this error coordinate, and this is a transformation matrix by which what we are doing, that we have transformed the system in the error coordinate and we have expressed the error dynamics. Now our objective will be, in the presence of this disturbance, that to design this control U such that this error dynamics can be stabilized. So basically it becomes a stabilization problem. Now fine, we want to converge asymptotically. So it is a asymptotic tracking error problem. So E is going to be 0 as T tends to infinity. But now the design what we want to do, that is divided in two parts. First we will design the controller in continuous domain, and then we will extend that design for the event triggered piece. So to do that, we have taken some assumption. So assumptions are that for the reference velocities v and omega are bounded, and we are not considering the entire state space. Instead of that, what we have done, we have restricted a domain D where xc is the mod of xc is less than xn, mod of y is less than ym, and theta mod of theta e is less than equal to pi. And also we have assumed that the disturbances which are matched disturbances, which is entering through input channel, which is also bounded, and we know that the upper bound of the disturbance. So now that's why here as you know that in case of sliding mode, it is a two-step design procedure. First we have to design a stable sliding surface, and then in the second step we have to design a control law by which we can force the system trajectory to move towards the sliding surface, and also when it will reach to the sliding surface we can maintain it forever. So now even if there is disturbance is present. So now here we have chosen a sliding surface which is nonlinear in nature, that is lambda into theta e plus v are tan inverse of ye and xc, and Vm and 2Vm means lambda is chosen in between Vm and 2Vm, and why this is taken to be clear from the stability group also. And then we have found out the derivative of the sliding surface, and why this derivative of sliding surface we have found out from, because we want to derive the control law from here, and once we make is not equal to 0, from there we can calculate the control law. But most interesting thing is that we have to take V1 inverse. So if you see the structure of V1, then you are finding that there is a singularity in control law. Means the control law means you can see that control law 9 requires the calculation of V1 bar inverse, this one, which causes a singularity when x equal to this. Thus, the continuous time controller can stabilize the system locally excluding this point. This singularity also can be addressed when we will do the event triggered design. So now here another important thing is that why we have chosen this nonlinear sliding surface. If we will choose a linear sliding surface, something like this, what will be the problem? Problem is that at that time you will have the term here lambda plus here xc will be equal to minus lambda into here. But if it is a nonlinear sliding surface, then you have the term, additional term, you have 1 plus y square, so it is a greater than 1. So what is the reason? Reason is that we want to maximize the region around that singularity point. Okay, so here this is thus the nonlinear sliding surface results in a bigger region for local stability of continuous time SMC design. So with this, we can guarantee that if we can choose the control gain K is greater than that magnitude of the disturbance, eta 1 is a positive scalar, then we can guarantee that the S0 is equal to be 0 in finite time, and if it is going to be 0 in finite time, then error is going to be 0 asymptotically. But in contrast to that, if we want to design the event triggered, and now we are motivated that why we need to design an event triggered control law. The same control law, if we want to here, this is the control law. if we want to design in event triggered context, then we have to redesign this control because the same game is not going to work. So we have to find out what is the stabilizing condition, and for that we have to redesign this control law to find out K here once again. And here all these variables what we are using in continuous domain, then at that time we have to use the sample version of that. To do that one, we are proposing this kind of setup where actually we have a wheeled mobile robot, and which have the three states, that is X, Y, and theta. Now we have to design an event condition, and this host computer is remotely located, and through the WMR to host computer it is connected with a Wi-Fi network, and these checked variables are the sampled variables. So with that we have to execute the control law, which we have to show that even if we are doing the that is irregular sampling or aperiodic sampling, that we are going to achieve the same performance what we are expecting from the continuous case. So to do that, here you see the same way we, as I told, that we are proposing the control law, which is the sample version, and now we have to design this K once again such that the similar kind of performance we can get with the sample signal. And now to do the design of event triggering, as I told, that we have to design a triggering law through which we will decide that when to sample. And here you can see that the beta t is defined as a weighted sum of the measurement errors of xc, ye, and theta e, and this C1, C2, C3, this the choices of C1, C2, C3 is done through the stabilization condition. And now here we are defining a set around the singular point, because as I told you that we have to avoid that singular point. So now here this is the region we have set around the singular point. Now it is thing is that already our earlier speaker pointed out also nicely that when we are designing a continuous time sliding mode control, we can guarantee that S1 and S2 both will be zero, perfectly zero in finite time. But in case of event triggered sliding mode control, we can ensure the practical stability. That's why it is known as practical sliding motion. At that time only we can guarantee that that system trajectories are going to be confined within a band, and the performance of the system will be going to be defined by this band. Means designer will choose that what is the band you want to be stay, and with that you can calculate the other parameters, and we will see that how the triggering the design parameter of the triggering law is going to influence the performance by calculating that band. So with this notion, we are telling that we are proposing that this is the triggering law, and this triggering law is a switching kind of triggering law, where you can say that gamma dagger is equal to rho if this xc, y, and theta e belongs to that set capital omega. Means what I want to mean that whenever you are near to that region of singular point, the control will be you can say that will be not updated. The same control law will be delayed such that that particular singular point can be escaped. And if we are able to have this stabilizing condition or the event condition, then we are saying that with the positive value of rho, the system trajectories are going to be drive toward the practical sliding mode, and the norm of S will be going to be bounded by alpha plus rho. And with that also we can say that this is the control gain, new control gain when we are using the event triggered setup. This is the gain we have to ensure by which we can say that the system trajectory will be confined inside the band. And also we can say that when C is going to be zero, at that time that, sorry, not XE is going to be bounded, then also it can be shown that YE and theta E also is going to be bounded, upper bounded by alpha plus rho, and also this. Okay. So now another important thing generally we used to ensure in case of event triggered design, that is, we have to ensure that the inter-event execution time should be upper bounded by a positive value. Why it is required? Because to ensure that one phenomena is called phenomena, which has to be avoided. Means in a finite time, you should ensure that there will be no infinite number of execution, and that can be by this condition that inter-event execution time is greater than equal to alpha plus gamma. And in details in our work, or in our paper, it has been derived that how you can ensure this. And also, it has been calculated that if there is a delay in the communication network is tau m, what is the maximum alpha hat you can choose by which you can ensure that okay, this, even if this amount of delay is there will be no significant deterioration in the performance. That also it has been calculated. Okay. So now with this theory, what we have done, we have tested this control algorithm in a Q-boat 2E, and these are the choices of parameters where we have defined the domain of interest by this, and that XE is less than 1.4, Y is 0.5, and theta is less than equal to 5. And also we have calculated the bounds of the Vm and omega n, and the sliding variable we have designed with this parameter, and these are the design parameters for the event triggered law. And with this, what I can show you that, okay, so here you see initial condition is chosen from this set such that we can ensure that we can exclude that particular singular point, and then this is the result we are showing you for for three cases I will show. That is, first is that elliptical case where we are finding that it is going to track in XY coordinate, and this is the sliding variable. You can see that sliding variable S1, S2 is not going to be 0 perfectly. Instead of that, it is going to be inside a band. Similarly, we can find that error is also going to be inside the band. They are not going to be 0. And this performance already we have seen. This is the initial condition we have started. And this is the inter-event execution time. And here you can see that at the beginning, the control computation is more, because that you are far from the, your initial condition is chosen in such a way that it is far from that your reference trajectory. But as it is going to settle down to its desired trajectory, you will find that the control our updates are more sparser. What we want actually that the control computation will be lesser, and this is the control effort you can see, and then this is the cumulative triggering instances. Okay, it will be near about 120 here, and this result is for the circular trajectory. We have taken another circular trajectory for that also. We are finding that after some time it is going to track. And this is the sliding variable and the error we have plotted. And then here also same kind of behavior we can see that here, that we can see that initially the control computation is more, but when it is converts to the reference trajectory, then we are finding that the sparser triggering are. In the similar result, we can see that the cumulative triggering in this case it is a little bit higher, that is 150 compared to the earlier one. And similarly, the same result I can show you for the U-shaped reference also. So this is the U-shaped reference we have taken. It will be deviation we can found here, and the satisfactory performance we have achieved using event triggered implementation of this sliding mode control for the WMR. And this is the cumulative triggering for the U-shaped reference. And to compare the performance of the system, we have introduced some of the performance indices, and then here you can see that this is the triggering parameter, and as the triggering parameter is higher, your number of triggering is, you see that significantly it is going to be dropped. But if you see the error is going to be more. Tracking error, the max you can find 3.05. So this is a design trade-off, that if you want more precise tracking performance, then you have to compromise with the number of triggering instances. It will be definitely more, and it is reflected here also. Okay. So now for the circular and U-shape trajectories also we have done that one. And if you want to see the experiment video, you can go through this YouTube link later on. After getting the slide, you can do that one. And as a conclusion, we can say that the design of event-triggered SLC has been proposed for an uncertain WMS system, because as you know that wheel mobile robot is an under-actuated system, as well as it having non-harmonic constant, due to that it having some inherent nonlinearity. So to encounter the nonlinearities as well as the disturbances, we have proposed to design a continuous lighting mode control, and after that to reduce the control computation, we have redesigned the continuous control in an event-triggered context. And for that, a triggering condition we have designed such that also in the design of event-triggered, we have designed the triggering law in such a way that the point of singularity can be escaped, and the event condition is redesigned to accommodate the communication delay, ensuring the closed loop stability. Okay. And also we have tested the performance of the controller in U-boat for the different trajectories. So if you want to know more about this, we have to and also we have some learning based approach for the tracking control of wheel mobile robot, that also can be seen. That is also in the context of event triggering, and these are the two references you can consider to see in details. And these are the few references we referred here to develop this work. So I think before time I have finished. So with that, I can now you can ask few questions to me that if possible I will address.
Long live India and France friendship.